go through this practice thing together. So we might not go through every single question because let me see how many there are. Yeah, there's 73 questions on here. I don't know if we'll have time to do every single question, but let's at least try to get as much of this done as we can before you guys go to take the final exam. All right, so before I just start working on some of these questions, especially the ones that you haven't seen in months, do you guys have any questions for me about anything? I saw that a lot of you sent me emails with your scratch paper. I haven't really looked through all of those emails yet, and I will after this meeting. And then I'm also going to go through your Chapter 11 test and give partial credit, of course. But any questions about anything before we just start practicing for the final?
The only one I had was for Chapter 11, question 9 on it.
Yeah, on the test, yeah. Yeah, that was a pretty tough one. And we can, here, I'll pull that one up before we start on this thing. Cool. Okay, so yeah, we'll look at this one real quick, just because I think this would be good moving forward anyway, because there's a lot of sections where you're having to find the centroid of something, regardless if this is a parametric thing, but sometimes you'll also have polar coordinates where you have to find the centroid, or just the normal Cartesian coordinates where we found the centroid. There's also finding the centroids of wires and centroids of areas. There's a bunch of center of mass stuff. So just going through this one real quick, the first thing that you're going to have to find is you're going to have to find that dm value. This is going to be the differential of the mass. Because this is a parametric equation, we're just looking at kind of a wire through space. And we don't have to graph this out if we don't want to, just because the math works out anyway. dm is going to represent a tiny little bit of mass on a small little subsection of our wire here. And to do this, we're going to be using that arc length formula, which is that square root thing. So it's the square root of the derivative of the x squared plus the derivative of the y squared. You can kind of think of it like a Pythagorean thing. So just to kind of write it out. And then we're going to add in like a little d t for the parameter at the end of this, for just to include the differential of the parameter. Okay, so again, this is the derivative of x. So looking at the x thing here, unfortunately, you're going to have to do a product rule. So it's going to be the first, that negative t, times the derivative of the second, derivative of cosine is sine, plus the second, which is the cosine, times the derivative of the first, which is a negative 1. Okay, that plus the derivative of this sine, which is cosine. Okay, same thing for the second one over here. We're going to have to do a derivative here, which is another product rule. So first, derivative of the second, plus the second, which is the sine t times the derivative of the first. That's going to be minus the derivative of cosine, which is sine. Okay, so I know that looks awful, and it kind of is, but we're just stuck with it. To clean this up, and it should clean up to be pretty nice, this is going to be a positive t sine t. The cosine and the sine cancel each other out, so it's just that t sine t squared, plus same thing's going to happen here. This sine t and this sine t cancel out, so we're going to end up with the t cosine t squared. Okay, and then just squaring these off, we're going to end up with a t squared sine squared t. This is also a t squared cosine squared t, and from each of those, we're going to factor out a t squared, which will leave us with sine squared plus cosine squared. And anytime you see a sine squared plus cosine squared, that's automatically going to be 1. So really, this is just the square root of t squared, which is just t. So this is what our differential is going to be. From there, what's that?
Yeah, I got that part of it. I
Yep.
didn't do it exactly that way, but I got the same answer.
Okay. From there, we have to find the three different integrals. We have the total mass, which is just integrating over the parameter of the differential that you just found. So integrating over t dt. This one's not too bad. It's 1/2 t squared from 0 to pi over 2, which is something. Pi squared over 8, I think. Just plugging it in my head. Yeah, it looks good. We also have to find those moments. So we have the moment sub x. The moment sub x is going to be kind of awful looking because it's that y wiggle dm. For y wiggle, just plug in the y value of your parameter. So this is going to be that t sine t plus cosine t, and then that whole thing times the differential up top here, t dt. And this is where it starts taking a while. Multiplying the t into all of this, it's the integral of t squared sine t plus t cosine t dt. And then from here, you could either split this up into two separate integrals and to do integration by parts separately, or what you could do is you could try to do an integration by parts just as the whole thing, but it's awful and I wouldn't do it that way. So unfortunately, it just takes a minute and you do integration by parts. Another thing that you could do, if you really want to get clever, is you can use your calculator, plug this into the calculator, and then just use the calculator to integrate from 0 to pi over 2 and get the value that way. I think the only problem with that is that you only ever get the decimal answer and not the exact answer, which is what they ask you to plug into the question. Okay, so integration by parts, right? Let's do these separately. So let's look at that integral of t squared sine t. This will be good practice for chapter 8 stuff anyway. So if I want to do integration by parts for this, I would let my u be the t squared and then my dv be the sine t dt. From there, I have to find my du, which would be 2t dt, and then my v, which would be the antiderivative of cosine, which is just a normal sign. Nope, negative. All right, plugging that in, we're going to do u times v, so negative t squared cosine of t, minus the integral of v times du here. So negative 2t cosine t dt. All right, and then unfortunately, we're going to have to do another integral by parts. Just to clean it up, these two negatives cancel out, and I can also pull out that 2. All right, and then integration by parts again. So let u be t. We're going to let dv be cosine of t, which means that du is just 1 dt, and then v, the antiderivative of cosine, is sine. Okay. And then we plug that integration by parts in for just the integral of t cosine t. So what we really have to be careful is that this 2 is on the outside. So that 2 stays on the outside, and on the inside, replacing this integral, we're going to do the integration by parts, which is uv t sine t minus the integral of v du. Which is just sine t dt. All right, and then just cleaning that up, we have the negative t squared cosine t out in front. We're going to have the plus 2t sine t from here. This negative integral of sine is going to change into a positive cosine, and then we have to bring the 2 in. So plus cosine of t. There we go. So there's the antiderivative of this first one. And if you're really clever about it, we actually just found this one as well, the other integral that we had to find, because the other integral that we had to find ended up coming into the second part of the integration by part. So we already have what the antiderivative is for that. So going back from this top integral, this integral we just found has antiderivative of this stuff, negative t squared cosine t plus 2t sine t plus cosine t, okay, plus this thing's antiderivative, which we had found in this parentheses here. So the t sine t, and then it's going to have a plus cosine t. All right, and then this we're evaluating from the limits 0 to pi over 2. Okay, so we plug pi over 2 into that, minus plugging 0 into that, and we should get some results here. Cosine of pi over 2 is just 0, so that whole term is 0. Plugging pi over 2 into this one, sine of pi over 2 is 1. So plugging the pi over 2 in for that t, we get 2 times pi over 2, which is just pi. Cosine is 0. This is going to give us a pi over 2 for the sine here. Plus cosine is 0. That's all going to be minus, plugging 0 into all of this stuff. We get a 0, 0, 1, 0, 1. So minus 2. And then you can try cleaning that up a little bit. So this would be 3 pi over 2 minus 2. Okay, so I'm kind of bored of the question already. And we would still have another integral to go. Right, because this is the moment sub x. We would have to find the moment sub y, doing the same kind of thing. But now that we have this, we could at least find the y component of the center of mass. Because the y component of the center of mass is going to be this thing, 3 pi over 2 minus 2. That thing divided by the total mass. The total mass we had found a little bit ago.
Pi over 8.
Yeah, pi squared over 8.
Yeah, pi squared over 8.
Well, close enough. And then you could try cleaning that up if you want to, but you could probably just plug that right in, just like that, and I'm pretty sure the homeworks would take that. So, well, they cleaned it up. This is what they got for their y value, but I promise you that this, for their y component, is just this. Yeah, so I know that was a long question, and I tried to throw one question on there that would take a while. But I hope it wasn't too hard. Does that help? Does that make sense for that question now, how to finish it?
Yeah, I ran into I got up to the whole x and y component of the moments, and it just completely just lost it. So.
Yeah, that's a hard integral, for sure. Okay, cool. All right, let's get away from chapter 11, because I will say that on the final exam itself, there isn't going to be too much of chapter 11 stuff. The majority of the final exam is coming from chapter 8 and chapter 10. And a lot of chapter 6 as well. Okay, so let's just start at the beginning of this practice, and let's just work through as much as we can work through today. I'll probably skip around a little bit just because I have a lot of the same types of question in a row, and I don't want to like overload with the same types of question. All right, but we're starting way back here. This was the first kind of problems we did back in chapter 6. Remember that the first couple of sections in chapter 6 were all about finding volumes. There was this way of finding volumes where we had solids created by planes, and then we also had solids that were created by rotation. So we'll look at some of those today. So for this first one, find the volume of the described solid. The solid lies between planes perpendicular to the x-axis at x equals 0 and x equals 8. The cross sections perpendicular to the x-axis between these planes are squares whose bases run from the parabola y equals negative 4 root x to the parabola y equals 4 root x. Okay, cool. first thing that I would do if I were you guys is that I would graph these two functions just to see what they look like in the calculator. I have a pretty good idea of what they look like. I think they're going to do this. So if we have our x and y plane, the positive 4 root x is just going to do this, just a normal square root function. The negative one's going to do this. So you're going to have this kind of parabola that's opening up to the right. This is going to go out to an x value of 8. So that's what these values are saying here, x equals 0 to x equals 8. And in between these parabolas, we're going to have squares whose cross sections are perpendicular to the x-axis. In other words, they're coming in and out of the page, whose bases run from these two parabolas. So the squares are going to be sitting on the xy plane, the base of the square, and it's going to come out of the screen to whatever it needs to come out of to be a square. All right, does everybody visualize what this shape is going to look like in their head? Mm-hmm. Squares coming in and out of the board where the bases run between the parabola lines here. Okay. Cool. So now we just do it. To find the area, to find the volume of solids that look like this, we're going to be integrating. Since we're integrating along the x-axis, my x-axis is going to go from 0 to 8. And we're just going to integrate over the cross-sectional areas as a function of x. So we need to find a formula for these cross-sectional areas. This question's not too bad because the cross-sectional areas that we're looking at are just these squares. So just to rewrite the integral, still going from 0 to 8. If my cross-sectional areas are squares and the base of those squares are going in between these two parabolas, that means that the base goes 4 root x down and then an extra 4 root x down. So in total, it's going 8 root x as the base. If this is a square, then to find the area of that square, we're just going to square the base to get the total area. Cool. So for every single value we are on the x-axis, if I plug that x value into this, it's going to give me the area. If I integrate all over the areas from 0 to 8, that'll give me the total volume. All right, and then just to finish off the integral here, so this is going to be the antiderivative. This is really 64x, which has antiderivative 32x squared from 0 to 8. So we just plug 8 into this and square it off. And I don't know, it's something. I don't have a calculator in front of me. I can use my phone. $2,048. Great. Okay, so is everybody okay with one like this? You're just integrating over the cross-sectional areas. Great, moving on. So I think the next couple of questions are very similar. Sometimes they are going to get a little bit more difficult. This one looks the same because, again, we have planes whose squares are the bases run from the semicircle. So that one's not too bad. All right, now we're into revolving stuff. So let's look at this one. So for this one, find the volume of the solid generated by revolving the shaded region about the x-axis. So here we have the function 5 secant, and then this is just going to be the function pi over 4. In my shaded region here, we're revolving it around the x-axis, so we're revolving it this way. Okay. We have a bunch of different ways of finding volumes when you're revolving something around. So we have the disk method. The disk method, the volume is just the integral over the pi, and then the radius as a function of whatever you need it to be a function of squared dx. So if we're revolving it around the x-axis, then it's going to be a function of x. If I was revolving it around the y-axis, it would be a function of y. We also have what we call the washer method. Washer method is really just an extended version of the disk method. This is just the integral of pi and then the outside radius squared minus the inside radius squared dx. And again, this could be a function of y if we were revolving around the y-axis instead. And then we finally, in section 2, talked about the shell method. The shell method was a little bit weird because the integral was integrating over the opposite variable. So if you're revolving around the x-axis, you would actually be integrating with respect to y. The formula to it was 2 pi, and then it was the shell length times the shell radius, and then again integrating over the revolving around the x-axis, we would be integrated with respect to y. So the length and the radius would have to be functions of y for this to work. Okay. Not only do you need to have these in front of you, so make sure. Oh, I think I emailed out a formula sheet. Did I? Like a final formula sheet to you guys? Have I done that yet? If not, then I will. I'll get a formula sheet to you guys, and these will be on there. So on the formula sheet, the formulas will be there. You just need to know when and how to use each formula. This problem would be a very good case for the disk method. It's a good case for the disk method because we're revolving around the x-axis and the border of my area is right up against the axis. If the border was not against it, we could use the washer method or the shell method. What's really important is knowing which slices are easiest to define. If I do vertical slices here, vertical slices are very easy because I'm going from my function 5 secant x down to 0 every single time. But if I were to try to do horizontal slices, they would be defined one way here at the bottom from 0 to pi over 4, but then up here from 5 secant x over to the vertical line. So we would have to define it 2 separate ways, which would just make it more complicated. Okay, so we're doing the disk method. We're doing the integral. Because we're integrating along the x-axis, we're going from 0 to pi over 4. And now we're using this formula, so pi. And then the radius with respect to x is just the vertical distance here, which is just from 0 to 5 secant x. So it's just 5 secant x. And it's that r value, that radius squared, dx. Okay, and then this shouldn't be too bad. So just to clean it up, you could take that pi out of there. You could also take the 5 squared out. I'll just leave it in there. So it's a 25 pi and then secant squared x. Secant squared is one of those nice ones that you should just be comfortable with at this point. The antiderivative of secant squared is tangent. So the antiderivative here will be 25 pi tangent of x, and that's going to be evaluated from 0 to pi over 4. If I plug pi over 4 into tangent, that's just 1, so I get the 25 pi, minus if I plug 0 in for the tangent, that's 0. So my answer should be 25 pi. Okay, so let's try and find another one that's a different method. That'd be a same thing. Here's a good one. So here, this would be a washer method one. So find the volume of the solid generated by revolving the shaded region about the x-axis. So we have our parabola. That parabola is the 16 minus x squared. We have this horizontal line and this vertical line making our shape, our area. We're revolving this over the x-axis, so we're revolving it this way. We could not do the disk method because my border is not up against my axis of rotation. We would have to either do the washer method or the shell method. It looks like both would work out pretty well here. I'm going to do the washer method because it already gives me my function in terms of x. So with the washer method, the volume is going to be the integral of the pi, and then it's going to be the outside radius squared minus the inside radius squared. And then this is going to be with respect to x, since I'm doing the washer method and revolving around the x-axis. The outside radius is the distance from the axis of rotation to the furthest possible point of your shape, which is going to be this horizontal line here at 16. So I'm just going to type in a 16 for the outside radius since it's a constant 16 the entire time. Minus the inside radius as a function of x, that's that 16 minus x squared, that parabola. Solve for y. Okay, the other thing that we haven't written down is the limits. And so if we're integrating along the x-axis, hopefully you can see that's going from 0 to 4. All right, and then you just have to clean this up and do the integral, which doesn't look too fun. So still the integral from 0 to 4. I'm going to go ahead and pull that pi like all the way out to the front so I can ignore it for a while. 16 squared is a number. I think it's 256. That was off memory. Minus, you'd have to FOIL this thing out. So it's going to be minus 256 minus 32x squared plus x to the 4th dx. All right, what's really nice is that those 256s look like they're going to cancel each other out. We're going to end up with a positive 32x squared and a negative x to the 4th. Okay, and then just to finish it off real quick, so antiderivatives, 32x squared is going to have an antiderivative of 32 thirds x cubed, minus x to the 4th will be to 1/5 x to the 5th. That's going from 0 to 4. Oops. I also forgot my pi already. There should be a pi way out in front of this. All right, and then you just plug in the numbers. Again, I don't have a calculator in front of me. I only have my calculator, and I don't really, or my phone. I don't really fully plug in this in, but it's not hard, right? Plug in 4, and you get a number. It's, if I had to guess, this one. Nope. That one. There we go. Got it. Second try. Don't do that on the test. So are these okay? Disk method, washer method, any questions about those? All right, cool. We haven't done a I need to practice with them. Yeah. Make sure you do that. We haven't done a shell method one yet. Let's see if we can find one that's a shell method. I guess we could always just force one of these to be a shell method. Now, this one specifically says use the shell method. So let's try this one. All right, use the shell method to find the volume of the solid generated by revolving the region bounded by the given curves about the given line. So here's our curves, y equals 3x, y equals x squared, and we're revolving that about the y-axis. I might use Desmos here, just so I can show you guys exactly what this looks like. 3x and x squared. Right, 3x, x squared? Yes. Cool. So this is going to be the region here between the blue lines and the red lines, and they want us to revolve that around the y-axis. So we're taking this and we're revolving it this way. Okay, so if we are using the shell method, remember that your slices for the shell method want to be parallel to your axis of rotation. So if our axis of rotation is the y-axis, we need to have vertical slices, which means that my slices are going to be going from the bottom blue line up to the red line. The blue line was the x squared graph. The red line was the 3x graph. All right. Just to go back to the formula for the shell method, it's here, and it'll be written kind of like that. So it's the integral of 2 pi, the length of the shells, and that needs to be in terms of a variable, more than likely, and then the radius of the shells also in terms of a variable. So just to have it in front of us, let me copy this down here. And then let's do it for this question. So we're going to have the integral. We'll worry about the limits here in just a second. the 2 pi. We don't know what the variable is going to be yet. Okay, so let's talk about the shell lengths. The shell lengths are going to be the lengths of your slices. So my slices are going from the 2 lines. And because they're going up and down, that means I need to do the top line minus the bottom line to get that length. The top line was 3x minus the bottom line x squared. So that's going to be my shell length, 3x minus x squared. The shell radius is going to be the distance from each of the slices to the axis of rotation. My slice is located at x, so that means that it is x units away from the axis of rotation. So my shell radius for this example is just x. All of this is in terms of x, which means we are integrating with respect to x. And if we are integrating with respect to x, that means that I have to go from 0 along the x-axis to this intersection point up here, which it says is 3, 9. So we're going from 0 to 3. Of course, to find that yourself, you could just set your 2 functions equal to each other and solve. So if I set 3x and x squared equal, you'll see that they intersect at 3. Okay, so that's setting up the integral, and that's what I care about the most for this stuff, is just making sure you can set up the right stuff. From here, doing the integrals isn't quite as important. Still important, just not as important. So I'm going to pull that 2 pi out to the front of my integral, and then we're going to have to distribute the x into here, so 3x squared minus x cubed dx. Okay, then we can just do the antiderivative at this point. So the antiderivative of 3x squared is going to be x cubed, minus x cubed is going to go to 1/4 x to the 4th. And this is going from 0 to 3. So if I plug 3 into that, I get 3 cubed, which is 27, minus 1/4 3 to the 4th. What is 3 to the 4th? 81, I think. So 81/4. All right. And then just go back to the homeworks to see if this matches anything. 27 minus 81/4 times 2 is definitely one of these numbers. I'm going with this one. I like that one. Oh, no. All right, it's got to be that one. All right, great. All right, so that was using the shell method. Make sure you don't get the disk, washer, and shell method confused, not only of when to use them, but how to use them and how to know whether you're integrating with respect to the x or the y. Oh, I just saw this button. I've never tried this before. Square root of x minus 2. That's cool. Okay. I never saw that before. That's neat. All right. Is everybody okay with this one? Shell method stuff? Can you explain and just set up changing to a function of y? Yeah, so if this was a question where it had this same area, but they wanted you to rotate it around the x-axis instead. So if you had to rotate this around the x-axis, then your setup would be a little bit different. It would still be this, right? The same formula. But now your shell length would be horizontal instead. So now the shell length, if I'm rotating it around the x-axis, would go from the red line to the blue line horizontally. We would have to find the difference of these two things, which means taking the blue line minus taking the red line. The problem, though, is that currently they are functions of y in terms of x, and they need to be the other way around. So this y equals 3x, I need to rewrite as x equals y over 3. And then this one, y equals x squared, I would have to write as x equals the positive square root of y. We only need the positive square root of y because that's this blue line here. The opposite side is the negative square root of y, and we don't need that part, so the positive one. All right, and then if we're finding the length of my shells are going between these lines, but you always have to take the bigger one, the one furthest to the right, and subtract it from the smaller one. So now, I don't know if I can like keep these on there. I think they're just going to disappear. You just have to remember, this one is square root y minus y over 3 for the radius. So square root y minus y over 3. Sorry, not the radius. That was for the height. But now we do the shell radius. The shell radius is going to be the distance from your slice to the axis of rotation. If my axis of rotation is the x-axis, my slices would be located at y as I move up and down. So I'm just going to plug in a y for the shell radius. And now we're integrating with respect to y, so we're just going to leave that dy there. And then you just do that. Oh, and then the limits, of course, as well, right? So my limits would go from the y value 0 up to this is the y value 9. So from 0 to 9. I hope that's what you meant. Does that help? Okay, cool. Yeah. Okay, so let's get away from volumes for a minute. Let's see what else they got. There's tons of other questions that you guys can practice with in here on those revolutions and finding volumes. All right, we're still in chapter 6. The next 2 sections are finding the length of curves, which is what this one is all about, and then finding the surface area of revolutions. There's just a formula to this, and the formula for this is very similar to the formula that we had for parametric stuff and for, what was the other thing? Polar stuff. So again, just a formula. It was the square root of your function derivative squared plus 1. Is that right? And this is going to be dy for this example because you're given the function in terms of y. Maybe it was the other way around, but I guess it doesn't matter. All right, you guys are going to have to look at that. Arc length integral formula. Oh yeah, okay, so I had it right, I just had them backwards, but it's the same thing. So 1 plus the derivative squared. So pretty much what I have written down here, I just have them the other way around. So whenever you have a question like this where you're trying to find the arc length, you need to take the derivative of the function, plug that in and square it, add the 1 under the square root, and then play around with it. For questions like this, there was always kind of a pattern to it. So let me show you that pattern. So first thing we need to do is we need to take the derivative of my function, which is just taking the derivative of this with respect to y's. So we would bring down the 3 halves. 3 halves times 1/3 is 1/2, and that's going to be y to the 1/2 power now. That's going to be minus the derivative of this, which is bringing down the 1/2. And now it's going to be y to the negative 1/2 power when you do the derivative. All right, that is what we're going to plug in for the x prime. So now my integral is still a square root, and it's going to be this thing squared. So that 1/2, just to copy it down, y to the 1/2 minus 1/2, y to the negative 1/2. That all squared plus 1. And now it's dy. So when you square this off, something kind of cool is going to happen. I say cool, it's probably not the right word. So just foiling this all out, we have 1/2 y to the 1/2 times another 1/2 y to the 1/2 which is 1/4 y. That's going to be minus, multiplying these two things together, the y to the 1/2 and the y to the negative 1/2 cancel out, and we just get a negative 1/4, but there's two of those because of the FOILing process, so 1/4 plus 1/4 is 1/2. That's going to be plus the last term multiplied by itself, which is 1/4, and then just y to the negative 1. And then don't forget the plus 1 out here. Okay, now my 1/2, my negative 1/2 and my 1 are going to add together. So we still have the square root. We still have that 1/4 y. Negative 1/2 plus 1 is positive 1/2 plus the 1/4 y to the negative 1. So that was just combining the negative 1/2 and the 1 together. And then the last step, and this is why they chose this question, because this shows up quite a bit for these types of questions, is that now we can factor this back out. This would factor out to be 1/2 y to the 1/2 plus 1/2 y to the negative 1/2 all squared. And because we have something completely squared underneath the square root, those two things cancel each other out. So now we're just going to have that 1/2 y to the 1/2 plus 1/2 y to the negative 1/2 dy. All right, and now you can just do this antiderivative, right? Take each of these exponents and raise them up by 1 and then divide, and then plug in your limits from 4 to 9. I don't really feel like finishing this problem because I don't think it's super important after this step. It's just that one trick to it with finding that perfect trinomial factored back down. Okay, so just keep in mind stuff like that may happen. Okay, just see what the right answer is. I'm trying to guess it. I bet it's 6. Nope. Well, okay, moving on. Here's another one where you're trying to find the length. This one's just asking you to set up the integral, not solve it all the way. Finding surface area. Okay, finding the surface area is almost identical to finding arc length. And basically what you do is you find the arc length and then you rotate that arc length around the axis of rotation. It's just another formula to it, and it's very similar to this formula. So I'm not going to bother doing an example of this one. Finding surface area again. Here we go. All right, so now we're getting into the really good stuff here of chapter 6. So the last two sections of chapter 6 were force and work problems, and then the center of mass problems. The first kinds of questions we had from this were these spring questions. Remember, the only thing that was super important with these spring questions was, who's that guy? Is it Hooke's? Hooke's law? Does that sound right? Hooke's law, which is just force is equal to the spring constant times the displacement. The other thing that was important is to find the work done of an object. If the force that's acting on the object changes as you move, then it's an integral, and it's just the integral over the force. Remember that if the force is constant, you didn't have to integrate, you would just multiply the force times the distance. But for changing forces like springs, you have to do this. So for this question, it gives you a force, 13,000 pounds, and it gives you a distance. You want to take these things and find the spring constant. Once you have the spring constant, then you have this side of the force, and then you just integrate over that to find the work done. All right, is that one all right without me actually plugging in the numbers to do that one? I think that one's pretty simple. So if you ever have a spring, these are your two formulas. First, find the spring constant. Once you have that, plug this kx in for the f and then integrate over it. Okay, let's get to more complicated stuff. Here's another kind of thing. So find the work done in winding up a 250-foot cable that pulls a 3 pounds per foot. This does not say anything about including the weight of the cable. The only thing, it doesn't have anything about the weight that the cable's holding, right? It's just the cable. This is also going to be a variable force. So you have to kind of take into consideration how much cable is left times the weight of the cable per foot to find the total work done and pulling it all the way up. So for this one, you just kind of have to come up with a force function. The force function for this is going to be the amount of cable left over. If X is the amount of cable that you've pulled in, then the amount of cable left over is going to be 250 minus X. That's the amount of cable that you have, and you want to multiply that by the weight of the cable or the density of the cable per foot. And so then you just integrate over this from 0 to 250. Okay, so again, another fairly simple one, but just using this integral thing here. Let's get into a really complicated one. Here, I know you guys love these. So here we have a tank. Inside this tank, we have a bunch of oil, and then the density of that oil. How much work does it take to pump the oil to the level of the top of the tank? And then they give us a bunch of numbers. Okay, so let's do this. Pumping liquid. Whenever you're doing this, there was not a formula that I gave you for this. Instead, I just kind of gave you a process. And the process goes like this. The first thing that you want to find is you want to find the differential of the volume. This is going to be, if you have a tank of liquid, you're going to slice that into a bunch of horizontal slices. The differential of the volume represents the volume of each of your slices. This you get by just finding the cross-sectional area as a function of how high up the area slice is times dy, where dy just represents the tiny little height of each of those slices. From there, then you want to find the force of each of your slices. And to find the force of each of your slices, you just take whatever you had previously, the volume, and you multiply that by the density. I don't know how I'm going to... Oh, there we go. Yeah, that was simple, right? That delta symbol. So just take whatever the volume was from the last line and then multiply it by the density. Not too much going on there. From there, you want to find the work. This is going to be the work it takes to remove one particular slice. That we find by taking the force that that slice is applying times the distance that it takes to get that slice out of the container. Okay, and then once you have this, you just integrate over that. All right, so just to go through it real quick again, you break it up into slices, find the volume of each slice as a function of y, find the force or the weight of that slice as a function of y, find the amount of work it's going to take to remove that slice, and then you integrate over that, of all of the slices. All right, so for this question that we have here, we have a vertical, right, circular, cylindrical tank. That's a fancy way of saying it's a cylinder. So we have a cylinder that is 28 feet high and 12 foot in diameter. When you slice a cylinder horizontally, you're just going to get a bunch of circles. So all of my slices are going to be circles with a diameter of 12. Okay. For problem 17. The volume of each of the slices is going to be the area of each slice. The area of a circle is pi r squared. If the diameter is 12, then my radius is going to be 6. So I'll write this as 6 squared for now. That times the differential of the height of each of my slices, which we're just going to call dy. It's just like an infinitesimally small distance along the y-axis for my cylinder. All right, so just to simplify this down, this is 36 pi dy. You're not always going to have constant ones here. We just happen to have constants because each of my slices is the same because it's a cylinder. If you have a container that like gets bigger or smaller as you go up, then you're going to have some y's in here because the area changes as you move. All right, moving on. Next we would have to find is the differential of the force. You can also think of that as the weight of each of these. And to find the weight, you just take the volume of each of them and then you multiply that by the density of the liquid. Oil weighs 60 pounds per cubic foot. So we're just going to multiply that by 60. And then 36 by 60 is a number, which I'm going to look up in my calculator or my phone. 2,160. 2,160 pi dy. Okay, so that is the weight of every slice. From here, we're going to find the amount of work it takes to remove the slice. That is taking the weight of the slice, the 2,160 pi dy, and then multiplying that by the distance to remove it. I need to draw something here. So with our system, it kind of depends on how you set it up. I would recommend for this kind of equation, just setting it up so that your container is sitting at the bottom, so that the bottom of the container is on the y-axis here. Great, so there's my container. Okay. If the height of the container was, oh crap, what was it? No, I can't move it. How do I move stuff? No. Oh, there we go. Okay, so if the height of the container is 28 feet, then the top here is going to be at 28 and my bottom is going to be at 0. So if I want to remove a particular slice, let's say we're at this location here. Oh, now I can't draw on it anymore. All right, forget it. Just pretend we're here, right? That there's a little circle right here that we're at, and that circle is located at y on the axis. To remove that, I have to go from y up to a height of 28, which is a total distance of 28 minus y. Okay, and then you just distribute into here. So I need to figure out what 2,160 times 28 is. A big number. 60,480. It's going to be times pi minus 2,160 pi y. And then this whole thing times dy, like all the way on the outside. All right, this is the work to remove just one slice. If I then want to find the total work, I would integrate over every possible slice, where my slices are going from 0 to the top of the tank at 28. And we're just integrating over this thing. Okay, and then you just do it, right? So that integral is not too bad, just some polynomial stuff. We're going to throw a y on this, minus this we're going to raise up to y squared and divide by that 2, and then plug in from 28 to 0. I don't really feel like doing that, because it's not hard. It's one of these. I'm guessing the biggest one. Oh no, that's the biggest one, isn't it? Darn it. Correct answer was B. All right, so the 2,000 one. Okay, so is that one all right? Any questions about finding the work to remove liquid from a container? Everybody okay with this process? Cool. And it's already 12 o'clock. Time like flies when we're doing some stuff. Well, let's just go real quick through the rest of chapter 6 type questions before we get out of here. And then we'll start at chapter 8 stuff tomorrow. This is another question, emptying a pool of a swimming pool. Find the fluid force. All right, so this is not one that we looked at today, but please go back and look at these. So this is where you have an object suspended underwater and you're looking for the force applied on the side of that object due to the water. For this one, again, you're doing slices, but this one does have a formula to it. So fluid force, the formula for this one is that the total force is the integral over, I just don't really know. I think it's the density times the strip length times the strip depth. I'm totally missing something here. dy. There's more to it than that. I feel like there's something else in there, but again, I'll send out the formula sheet and you're just plugging stuff in. Your strips always have to be horizontal, so then the length is just whatever the formula needs to be to get across the object. The depth is going to be the vertical distance from the top of the surface down to wherever your strip is located. Okay, so please go back and look at fluid force problems because you might see one like that. And then the last thing that we saw here from chapter 6 was center of mass stuff. This is just asking you to find the moment, but of course taking that further, then they would ask you to find center of mass. And we already did a center of mass question earlier today. It's just that this one isn't with parametric or polar type stuff. This was just with the generic Cartesian coordinate system, and then you're finding it from there. So hopefully not too bad, but it's the same process. And that was it for chapter 6. So chapter 6 is a big one, and there is a lot of stuff in there, but we'll probably see more questions coming from chapter 8 and chapter 10, like I said, and then this will just be kind of sprinkled all over the place. I would say there's maybe 4 to 5 questions from just chapter 6 on the final. So please go back and look over the stuff because it is important. All right, it's already 12, and I have other obligations, so I need to get going here pretty soon. But is there any last questions of anything that we talked about here from the chapter 6 stuff from this practice assignment? You bet.
No, I think I'm good.
Okay, so I recorded this one. If you want to go back and look through it, I'll put it up on Moodle. I'm also, don't forget, tomorrow at 11, I'm going to be doing another one of these, and we'll start the chapter 8 stuff. If you can't make it, I'll record that one as well, and you can look over it later. And then Thursday, we'll hopefully be doing the chapter 10 stuff. And a little bit of chapter 9 we need to sprinkle in there as well. Okay, thanks for coming today. There was a lot of you that showed up. It's good. Gives me hope that all of you are going to do really good on the final exam itself. You don't have to wait till Friday to take the exam if you don't want to. You can take it any time between now and Friday. As soon as we get off here, I will be emailing out that formula sheet for the final exam. So make sure you look out for that. And then other than that, hopefully I'll see everybody tomorrow. If not tomorrow, then Thursday. If I don't see you at all, then good luck on the final. And hopefully I'll see you around in Calc 3. Okay, cool. Thanks for coming. Bye. Bye, everybody.